A nebula is a distinctively luminous region of the interstellar medium, which may be made up of cosmic dust, neutral, neutrally ionized, or molecular hydrogen. Nebulae are frequently areas where stars are being formed, as seen in the Eagle Nebula's pillars of creation. The gas, dust, and other material formations in these areas clump together to form denser regions, which draw in more matter and finally reach a density where stars can form. Planets and other planetary system objects are then supposed to be formed from the leftover material. Most nebulae are enormous in size, some have diameters of hundreds of light years. When close by, a nebula that is visible to the human eye from Earth would appear bigger, but not any brighter. Early astronomers were unaware of the Orion Nebula, the brightest nebula in the sky, which can be seen with the unaided eye and covers an area twice the angular diameter of the full moon. Most nebulae are much less dense than any vacuum formed on Earth, despite the fact that they are denser than the space around them. An Earth-sized nebular cloud would have a total mass of only a few kilograms. The densest nebulae can have densities of 10,000 molecules per cubic centimeter, in contrast to the air humans breathe, which has a density of about 1,019 molecules per cubic centimeter. While some nebulae are so diffused that they may only be seen with long exposures and specialized filters, others are visible owing to fluorescence created by embedded blazing stars. Some nebulae have fluctuating T-Tauri star illumination. Initially, any diffused astronomical object, including galaxies outside the Milky Way, was referred to as a nebula. Before the real nature of galaxies was established in the early 20th century by Vesto Slipher, Edwin Hubble, and others, spiral galaxies in general were referred to as spiral nebulae and the Andromeda Galaxy as the Andromeda Nebula. The majority of nebulae are connected to stars and lighted by starlight, as Edwin Hubble discovered. He also assisted in classifying nebulae according to the kind of light spectrum they emitted. William Huggins began analyzing the spectra of roughly 70 nebulae in 1864. He discovered that about a third of them exhibited gas emission characteristics. The rest were believed to be made up of a mass of stars because they had a continuous spectrum. When Vesto Slipher demonstrated that the spectra of the nebula that enveloped the star Merope resembled those of the Pleiades open cluster, a third category was added. As a result, the nebula emits light from reflected stars. Slipher and Edwin Hubble kept gathering the spectra from many nebulae, discovering 29 that displayed emission spectra and 33 that included the continuous spectra of stellar light. Hubble declared in 1922 that almost all nebulae are connected to stars and are illuminated by starlight. Additionally, he found that emission spectrum nebulae are almost always connected to stars with spectral classifications of B or hotter, including all main sequence stars of the O-type, whereas nebulae with continuous spectra are connected to stars with cooler temperatures. Hubble and Henry Norris Russell both came to the conclusion that the nebulae encircling the hotter stars are altered in some way. The many forms of nebulae have a wide range of formation processes. While some nebulae are created by stars, others are formed from gas that is already present in the interstellar medium. Giant molecular clouds, the coldest, densest phase of interstellar gas, which can develop through cooling and condensation of more diffuse gas, are examples of the earlier situation. Planetary nebulae, which are examples of the latter situation, were created from material ejected by a star during the last phases of its stellar evolution. A type of emission nebula known as star-forming regions is connected to enormous molecular clouds. When a molecular cloud falls over from its own weight, stars are created. In the core, massive stars might emerge, and their ultraviolet radiation ionizes the surrounding gas, making it visible at optical wavelengths. The shells of neutral hydrogen surrounding the H2 region are referred to as the photodissociation area, while the region of ionized hydrogen surrounding the massive stars is referred to as a H2 region. The Orion Nebula, Rosette Nebula, and Omega Nebula are a few examples of star-forming nebulae. A few million years after star formation, the nebula may be destroyed by supernova explosions of big stars, stellar winds, ultraviolet radiation from massive stars, or outflows from low-mass stars that destabilize the cloud. Other nebulae are created by supernova explosions, which are the latter stages of the lives of huge, short-lived stars. The energy and compact object that the supernova center generates then ionize the materials that were released during the explosion. The Crab Nebula in Taurus is one of the greatest instances of this. The supernova event is known as SN 1054 and was noted in the year 1054. The neutron star in the center of the compact object that resulted from the explosion is located in the Crab Nebula. The majority of nebulae are what are known as diffuse nebulae, which are expansive and lack clearly defined borders. Emission nebulae, reflection nebulae, and dark nebulae are the three categories of diffuse nebulae. The two types of visible light nebulae are emission nebulae, also known as H2 regions, which produce spectral line radiation from excited or ionized gas, mainly ionized hydrogen, and reflection nebulae, which are visible mostly because of the light they reflect. Reflection nebulae are close to stars and reflect light from them, but they do not produce much visible light on their own. They are known as dark nebulae. Comparable nebulae that are not lighted by stars do not produce visible radiation, but they can be found as opaque clouds that obscure light from illuminating objects behind them. Although the optical visibility of these nebulae varies, they are all prominent sources of infrared emission, primarily due to dust within the nebulae. Planetary nebulae are the remains of mid-mass stars, which range in size from 0.5 to 8 solar masses at the end of their stellar life. Strong stellar winds cause evolved asymptotic giant branch stars to shed their outer layers, generating gaseous shells and leaving the star's core behind in the form of a white dwarf. Expelled gases are excited by radiation from the hot white dwarf, creating emission nebulae with spectra resembling those of emission nebulae found in star formation zones. Since most of the hydrogen in them has been ionized, they are H2 regions, yet planetary nebulae are denser and more compact than nebulae seen in star formation regions. The first astronomers who saw them were initially unable to tell them apart from planets and tended to confuse them with planets, which were of greater importance to them, giving them their name. A planetary nebula is predicted to form 12 billion years after the birth of our Sun. An astronomical object known as a protoplanetary nebula, PPN, is a brief period in a star's rapid stellar evolution that occurs between the late asymptotic giant branch LAGB phase and the planetary nebula PN phase. The star loses mass during the AGB phase and emits a hydrogen gas disk around itself. The star moves into the PPN phase at the conclusion of this phase. The center star energizes the PPN, causing it to generate powerful infrared radiation and develop into a reflection nebula. The shell is shaped and shocked into an axially symmetric structure by collimated stellar winds from the core star, which also create a swiftly flowing molecular wind. The temperature of the central star determines the precise point at which a PPN transforms into a planetary nebula, PN. The PPN phase lasts until the core star is hot enough to ionize the surrounding gas, which happens when its temperature hits 30,000 K. When a high-mass star reaches the end of its lifespan, a supernova happens. The star collapses after nuclear fusion in its core is stopped. The star explodes as the gas going inward either bounces back or becomes so intensely heated that it spreads outwards from the core. A peculiar diffuse nebula called a supernova remnant is created by the gas shell's expansion. Although ionized gas is largely responsible for the optical and X-ray emission from supernova remnants, a significant portion of the radio emission is a type of non-thermal radiation known as synchrotron emission. High-speed electrons oscillating in magnetic fields produce this emission. This is all for today. Thank you for staying with us. Don't forget to like and subscribe our channel. See you soon.